Good morning, I am Sena. In this lecture, we are going to discuss about root locus problem. This topic is present in the subject control system. Sketch the root locus diagram of the following open loop transfer function. G of s h of s is equal to k divided by s into s plus 2 into s plus 5. This question is asked in an university November-December 2005. Step 1. First we have to identify the number of poles and zeros that is been given in the given open loop transfer function. In this problem, the number of poles are at s is equal to 0, minus 2, minus 5. We are having 3 poles. And in this problem, the number of zeros are z is equal to 0. Now we are going to identify the number of separate root loci, that is number of branches. Here the number of branches is equal to number of poles because the number of zeros are 0. Then we are going to identify the starting point of the root locus. Generally, the starting point of the root locus branches are from the poles. Here, the poles are 0, minus 2 and minus 5. So, the starting point of the root locus is 0, minus 2 and minus 5. The terminating point of the root locus branches are at zeros. But in this problem, we have no zeros. So, root locus branches terminates at infinity. Let us see the location of poles. This is the representation of the location of poles in the root locus. Here, we have 3 poles at 0, minus 2 and minus 5. Mark these poles in the root locus. Now we are going to identify the parts of the root locus. Consider the point P1 in the root locus. To the right hand side of the point P1, the sum of poles and zeros are odd. That is, only one pole is present to the right hand side of the point P1. Therefore, the point P1 is the part of the root locus. Now consider point P2. To the right hand side of the point P2, the sum of poles and zeros are even. That is, 2 poles are located to the right hand side of the point P2. Therefore, P2 is not the part of the root locus. Now consider point P3. To the right hand side of the point P3, the sum of poles and zeros are odd. That is, to the right hand side of point P3, we have 3 poles. So, P3 is the part of the root locus. Now we are going to identify the number of asymptotes and angle of asymptotes. Formula for calculating the number of asymptotes is n suffix a is equal to the number of poles minus number of zeros, that is p minus z. Here we have 3 poles and 0 zeros. Therefore, the number of asymptotes is equal to 3 minus 0, that is 3. Now we are going to calculate the angle of asymptotes. Formula for calculating the angle of asymptotes is theta suffix n is equal to 2 into 2n plus 1 into pi divided by p minus z, where n is equal to 0, 1, 2 and it goes on up to p minus z minus 1. Here n is equal to na, that is p minus z. So that is 3. Therefore, we have to consider the value of n as 0, 1 and 2. For n is equal to 0, the theta suffix 0 is equal to 2 of 0 plus 1 into pi divided by 3 minus 0. That is, its angle is 60 degree. Now consider for n is equal to 1. Theta 1 is equal to 2 into 1 plus 1 into pi divided by 3 minus 0. Its angle is 180 degree. Now we are going to calculate for n is equal to 2. that is theta suffix 2 is equal to 2 into 2 plus 1 into pi divided by 3 minus 0. Its value is 300 degree. Now we are going to calculate the centroid value. Centroid is a point where the angle of asymptotes intersects on the real axis. The centroid may be a part of a root locus or it may not be a part of a root locus. The centroid is represented by a letter sigma. Formula for calculating the centroid is sigma is equal to the sum of real parts of poles minus sum of real parts of zeros divided by p minus z. In this problem, we have 3 poles, that is 0, minus 2 and minus 5. There is no zeros, so the real parts of poles are 0, minus 2 and minus 5 and real parts of zeros are 0. Therefore, the centroid is equal to 0, minus 2, minus 5 minus 0 divided by 3 minus 0. Its value is minus 7 divided by 3, that is minus 2.3. Now we are going to determine the breakaway point. Breakaway point is a point where the root locus intersects on the real axis. The breakaway point must be a part of a root locus. Therefore, we have to calculate the breakaway point. Consider the characteristic equation 1 plus g of s h of s is equal to 0. The g of s h of s is the open loop transfer function. Its value is given in the problem. Here we have g of s h of s is equal to k divided by s into s plus 2 into s plus 5. Therefore, the characteristic equation is 1 plus k divided by s into s plus 2 into s plus 5 is equal to 0. If we simplify this equation means we obtain s into s square plus 7s plus 10 plus k is equal to 0. That is k value is equal to minus s into s square plus 7s plus 10. If we further simplify means k is equal to minus of s cube plus 7s square plus 10s. In order to determine the breakaway point, we have to differentiate the k value with respect to the s and we have to equate this to 0. K is equal to minus of s cube plus 7s square plus 10s. We have to differentiate this k value with respect to the s and we have to equate this dk by ds is equal to 0. That is, after differentiating the k value, we obtain minus 3s square minus 14s minus 10. We have to equate this minus 3s square minus 14s minus 10 to 0. We simplify this equation means we obtain 3s square plus 14s plus 10 is equal to 0. We have to solve this above quadratic equation. If we solve means we obtain two values, that is s is equal to minus 0.88 and minus 3.78. Out of these two breakaway points, we have to identify the valid breakaway point. The valid breakaway point is minus 0.88 because the breakaway point must be the part of the root locus. Now we are going to identify the intersection of the root locus with the imaginary axis j omega. Consider the characteristic equation 1 plus g of s h of s is equal to 0. We get s cube plus 7s square plus 10s plus k is equal to 0. We have to identify the coefficients of this given polynomial. From that, we have identified the coefficients as a0 is equal to 1, a1 is equal to 7, a2 is equal to 10, a3 is equal to k. With the help of these values, we are going to construct the Routh's array. Routh's array comprises of to have intersection on the imaginary axis. In the Routh's array, any one row should be 0. Let us make S1 row to be 0. That is, 70 minus k divided by 7 is equal to 0. If we simplify this equation means 70 minus k is equal to 0. After simplifying means the value of k is equal to 70. Now consider the auxiliary equation 7s square plus k is equal to 0. Substitute the value of k as 70 in the above equation. We get 7s square plus 70 is equal to 0. That is s square plus 10 is equal to 0. If we further simplify the given equation means we obtain the value of s is equal to plus or minus j square root of 10, that is plus or minus j 3.2. This plus or minus j 3.2 is the point where the intersection of the root locus is on the imaginary axis. The complete root locus is shown in figure. Here is the root locus representation. In this root locus, we have the centroid. Its value is minus 2.3. The centroid may be a part of a root locus or it may not be a part of a root locus. The centroid is a point where the angle of asymptotes intersects on the real axis. And we have identified the breakaway point. Here, the breakaway point is minus 0.88. The breakaway point must be a part of a root locus. The breakaway point is the point where the root locus intersects on the real axis and the root locus intersects on the imaginary axis at plus or minus j 3.2. It is indicated in this graph. Let us solve next root locus problem. The problem statement is: obtain the root locus for a unity feedback system with open loop transfer function g of s h of s is equal to k divided by s into s square plus 6s plus 25. This question is asked in an university May-June 2006. Here in this problem we are having three poles. One is at the real axis, that is s is equal to 0, and the other two poles are complex poles because we are having a quadratic equation s square plus 6s plus 25. This quadratic equation is present in the denominator. This provides a complex poles minus 3 plus j4 and minus 3 minus j4. Here we are having no zeros. Now we are going to determine the number of separate root loci, that is branches. Here we are having three poles, so the number of poles capital P is equal to 3. Then we have to identify the starting point of the root locus. The starting point of the root locus are from the poles 0, minus 3 plus j4 and minus 3 minus j4. The terminating point of the root locus is at 0. Here we have no zeros, so the root locus terminates at infinity. Consider point P1. To the right hand side of the point P1, we have only one pole located at s is equal to 0. Therefore, the sum of poles and zeros are 1. It is in odd. So, P1 is the part of the root locus. This is the representation of the root locus. Now we are going to determine the number of asymptotes and angle of asymptotes. Formula for calculating the number of asymptotes is capital N suffix A is equal to capital P minus capital Z, that is 3 minus 0. Its value is 3. Now we are going to calculate the angle of asymptotes. Formula for calculating the angle of asymptotes is theta suffix n is equal to 2n plus 1 into pi divided by p minus z, where the n starts from 0, 1, 2 and it goes on up to p minus z minus 1. Here n is equal to n suffix a, that is p minus z is equal to 3 minus 0, that is 3. Therefore, we have to consider the value of n as 0, 1, 2. Now, we are going to calculate the angle of asymptotes for n is equal to 0, that is theta suffix 0. If you substitute the value of n as equal to 0 means we get the angle of asymptote as 60 degree. Now if you are substituting the value of n is equal to 1 means we get the angle of asymptotes theta suffix 1 is equal to 2 of 1 plus 1 into pi divided by 3 minus 0. It provides 180 degree angle of asymptotes. If you substitute n is equal to 2, the angle of asymptote value is 300 degree. Now we are going to determine the centroid value. Centroid is represented by a symbol sigma. Formula for calculating the centroid is equal to sum of real parts of poles minus sum of real parts of zeros divided by p minus z. Here we have three poles. One pole is a 0 and another two are the complex poles. The complex poles comprises of real part as well as the imaginary part. Therefore, for calculating the value of the real parts of poles, we have to consider 0, minus 3 and minus 3. If you substitute the values means we obtain the centroid as minus 2. Now we are going to determine the breakaway point. Formula for calculating the breakaway point is 1 plus g of s h of s that is equal to 0, where g of s h of s is open loop transfer function. It is given in the problem, that is 1 plus k divided by s into s square plus 6s plus 25 is equal to 0. If you simplify the above equation means we obtain s into s square plus 6s plus 25 plus k is equal to 0. If you further simplify means we get k is equal to minus s into s square plus 6s plus 25. It provides k value as k is equal to minus of s cube plus 6s square plus 25s. To find the breakaway point, we have to differentiate the value of k with respect to the s and equate to 0. That is dk by ds is equal to 0. If you differentiate the k value means we obtain minus 3s square minus 12s minus 25. We have to equate this value to 0. That is 3s square plus 12s plus 25 is equal to 0. Now we have to solve the above quadratic equation. We get s is equal to minus 2 plus or minus j 0.5 square root of 39. This point is not on the root locus, therefore there is no breakaway point. Now we are going to determine the intersection of the root locus with the imaginary axis. For that we have to consider the characteristic equation 1 plus g of s h of s is equal to 0. That is 1 plus k divided by s into s square plus 25 is equal to 0. If you simplify this equation means we obtain s cube plus 6s square plus 25s plus k is equal to 0. Consider this equation and we have to identify the values of a0, a1, a2 and a3. That is a0 is equal to 1, a1 is equal to 6, a2 is equal to 25 and a3 is equal to k. Now we are going to construct Routh's array. Routh's array is constructed with the help of the values a0, a1, a2 and a3. This is the Routh's array. To have intersection on the imaginary axis, any one row should be 0. Let us make S1 row to be 0. That is 150 minus k divided by 6 is equal to 0 means we get 150 minus k is equal to 0. If we further simplify this equation means we obtain the value of k is equal to 150. Now consider the auxiliary equation, that is 6s square plus k is equal to 0. If you are substituting the value of k is equal to 150 in the above equation means we get 6s square plus 150 is equal to 0. That is s square plus 25 is equal to 0. We get the value of s is equal to plus or minus j5. The root locus intersects at the imaginary axis at s is equal to plus or minus j5. We have complex poles, so angle of departure has to be calculated. Consider point P2. Phi of P1 is equal to minus 180 degree minus tan inverse of 3 by 4. Its value is minus 143.13 degree. Now, phi of P3 is equal to minus 90 degree. Therefore, sum of phi P is equal to phi of P1 plus phi of P3, that is minus 143.13 degree minus 90 degree. Its value is minus 233.13 degree. The sum of zeros are 0. Therefore, phi is equal to sum of phi P minus sum of phi Z, that is minus 233.13 degree minus 0. It is minus 233.13 degree. Therefore, the angle of departure is equal to 180 degree minus of 213 to 33.13 degree. It is minus 53.13 degree. This is the angle of departure calculation diagram. The complete root locus is provided below. In this problem, we have centroid at minus 2 and there is no breakaway point in this problem. The angle of departure is minus 53.3 degree.